Hey there, this is Math 8, Unit 3, Lesson 11, called Equations of All Kinds of Lines. And so we're going to be writing equations today for vertical and horizontal lines. Alright, we began today's lesson in class looking at which one doesn't belong, and you had a series of lines or pairs of lines here in A, B, C, and D. And you should have had a conversation in class about which one doesn't seem to belong in terms of how things look. Okay, we could look and say that, well, a couple of them at least have a positive slope going up, and that one's going down, that one goes straight across. And so we could look and say, well, there's not a difference there. But one big thing stands out, and that is that when you look at the lines, these lines here tend to be parallel lines. They tend to be running in the same direction, parallel to each other. Whereas these guys here, if you were to continue this on and on and on, we probably would get a point at which they cross because they are not parallel lines. And so if you're looking at them from that perspective, we would probably say that B is the one that doesn't really belong with the others because it's the only one that is not a set of parallel lines. Okay, and that's kind of a key thing there in that. So parallel lines. Sorry for my spelling. All right, look at the next page, 11.2, all the same. It says to plot at least 10 points whose y-coordinate is -4. So the y-coordinate would be, y is going to be here. And so if we take out, let's go ahead and get out my red for now, -4, what we're saying is let's plot points along the negative, or y equals -4. So y equals -4, y equals -4, -4, -4. And we can plot 10 or a million, it really doesn't matter. We could plot a bunch of them there just like that. So what do we notice about them? Well, we notice that the points are on a line, right? That's one thing we might notice. They seem to be going in a line like so. We can also perhaps notice that they are also parallel to the x-axis, right? Our x-axis is right here, and we would say that these points are parallel to the x-axis, okay? So when we look at this, we have coordinate -4. When it says write an equation that which equation makes the most sense to represent all the points with y coordinate -4, and explain how you know. Well, when we look at these equations here, the one that makes the most sense is going to be for where y simply equals -4, right? Because y just has a value of -4. That's just where it's going to be at. Y equals -4 there and there. There's no slope. There's nothing going on that, and really there's nothing with the x values at all that we could say. That really makes a lot of sense there. So we would probably go with something along those lines. When we turn the page, we see that it asks us to then plot at least 10 points whose x-coordinate is 3. Alright, so we look for the x-coordinate of 3. In that case here, the x-coordinate right here is 3. Here's where 3 is at. And so I plot those like so, and plot them like that. Then what I end up with is something very similar to the y-coordinate. I can see, first of all, similar things, that it has points that seem to be in a line, in this case a vertical line. We can see that it runs parallel to the y-axis right there. Okay, that's what we have so far. So that's the same kind of thing we noticed, similar things. We got parallel, this case here, parallel to y-axis. They seem to be in a line of some sort. And in this case, in terms of an equation that works to represent those points along there, we would say it's going to be x equals 3. Because wherever x equals 3, we have a point. When x equals 3, we have a point all the way around there. Okay? So it's kind of interesting. When you have x equals 3, you end up with a line that goes vertical, right, at 3. When you have x equals, or y equals a number, then you go horizontal. So if I was to graph the equation, let's just do this here. Here's a little coordinate grid here. And here's x minus 2. Here's y. 2, 3, 4, 5. So here's 5, here's minus 2. Right, like so. If I was to graph the equation x equals -2, okay, when x equals -2, where does x equal -2 at? X equals -2 right here along that line. That's where it equals minus 2 at. Where does y equal negative 5, or positive 5? Y equals 5 is right there. So in terms of an equation for a line, y equals 5 looks like this. Ends up being a horizontal line. Whereas x minus 2 equals negative 2 ends up being a line here, which is a vertical line. So it's just kind of interesting to think about that when you're talking about x equaling a number, you end up with a vertical line. And when you talk about y equaling a specific number, you're talking about a horizontal line. So just kind of keep that straight in your head a little bit, okay? Let's look at this next one. Are you ready for more? Because it's a good little question. It says, draw a rectangle with vertices at 2, 1, 5, 1, 5, 3, and 2, 3. Okay, so I did a little quick sketch like this. I went, well, let's just draw this like this and make my points here and here. And I know that for my x values, I need to get 2, 5, and 2. So let's get up to 5. So 1, 2, 3, 4, 5. My y values have a 1, and up to 3. So I need to go 1, 2, 3, up to there. And so for my points, I can see that I have 2, 1, which is going to be right there. I have 5, 1, which is right there. I have 5, 3, which is here. And 2, 3, which is there. So those are the points of the vertices for the rectangle, which would look something like this. It's not a great rectangle, it's not perfect, it's a sketch. Okay? For each of the 4 sides of the rectangle, write an equation for a line containing the side. So we're looking for an equation for each one of those lines there that contains that side. So let's just start with our y ones. This line right here, the equation for this line that would go across this point right there, that line there, we have to look at where does it cross. It crosses the y-axis at 3. So the equation for this line would be y equals 3. In a similar way, this line right here that would fill in the bottom part of the rectangle crosses at 1. We would say that y equals 1. Okay, good with that so far? That's what we got so far. Now let's take a look then here at the vertical side, because here, this line that makes that side of the rectangle crosses at x equals 2. So we would say that's at x equals 2. And this one crosses right there, where what? Where x equals 5. So those become the equations of the lines that surround that rectangle, or the 4 sides of that rectangle, like we saw before. For number 3, it says that a rectangle has sides on the graphs of x equals -1, x equals 3, y equals -1, and y equals 1. Find the coordinates of each vertex. So now we're going the opposite direction. So a great little question here. So if I take my coordinate grid like this and just sketch one out real quick, like so, we have x at a -1. We also have x at positive 3. So 1, 2, 3. So there's 3 and there's 1. We have y at -1 and we have y at positive 1. So what we're saying is that for the x equals -1, we're going to have a line that goes somewhere through here. That's our line there at 1. We have a line at 3 that goes through there. Okay, that's x equals 3. Here's x equals -1. And then for the y, we have y equals -1 here. Right? Y equals -1. Looks like that. Then we also have y equals 1, which goes through there. Y equals 1. And what they're asking us to do is to identify the coordinates of each vertex. That point, that point, that point, and that point. So to do that, what we're talking about then is we're going to take a look. We have over here, let's begin here. This point right here is at 3, 1. So our point right there is at 3, 1. Over 3, up 1. My point right here is also over 3, but I'm at now -1. My point right here, I've gone over -1 on the x thing, and on the y, I'm at -1. And over here, I'm still at -1 on the x value, but I'm at +1 for the y value. So those become the 4 coordinates for each of the vertexes for that rectangle right there. So kind of a cool little question to kind of put things together for you. Let's look at part 3. Part 3 is a great little problem here, especially in terms of what it ends up looking like at the end. So hang in there with me for a bit, all right? It says, first of all, there are many possible rectangles, and by many we mean many rectangles whose perimeter is 50 units. Complete the table with lengths L and widths W of at least 10 such rectangles. All right, and I don't know if I'm going to do all 10 of them, but just to get you an idea here. So if we're looking about a rectangle perimeter of 50, what it really means is I have to think about a perimeter is a rectangle is going to be a length and a width, and whatever that length and width is, I'm doing it 2 times, right? So it's 2 times that. So if I take the 50 and divide it by 2, my length and width really need to add up to something that equals 25. So for example, if I have a length of 1 and a width of 24, my total length and width together is 25, but since I multiply it by 2 to get the perimeter, I end up with 50. All right, does that make sense? So as long as these two numbers, the sum of them is 25, then I'm going to have a possible rectangle. All right, so some other options you might have. You could have 4 and 21, that equals 25. You could have a 7 and an 18 equals 25. You could have a 12 and a 13, which equals 25. And then I can keep going, I can flip it and go the other way, right? I could do a 18 and 7. I could do a 21 and 4, and I can do a 24 and 1. Got the idea? One other one I can think about doing, just because of how this works out here, I look at the next problem. The next problem actually has one drawn here that is at 15 and 10. So that's the point that's right here at 10, 15. So we could have 15 and 10, but we could also have 10 and 15. All right, just to give you some examples. Again, there are many different ones you can have. These are just examples of some that would work. Let's look at number 2, because that's the important part of this problem. The graph shows one rectangle whose perimeter is 50 units and has its lower left vertex at the origin, so down here, so that's the other vertex there, and 2 sides on the axes. So we have 2 sides here and a corner at the vertex. On the same graph, draw more rectangles with perimeter 50 using the values from our table up here. Make sure that each rectangle has a lower left vertex at the origin and 2 sides on the axes. All right, so this is kind of a cool problem because we look at the first one. The first one is at 1, 24. So it has a length of 1 and a width of 24. Here's my width down here, and my length is here. So my first one would actually go out 1 all the way to 24, which is right there. So that's my first one. Now if that's my first one, what's kind of cool is I could then do the other one, which would be 24 and 1, which would look something like this. 24 and 1, right? Yeah, I don't need to really outline this outside edge because they all share that one. So that's going to be those first 2 ones right there. Okay, the next one I have a length of 4, which is here, and a width of 21. So here's 4, and 21 comes out to 1, 2, 3, 4, out to that point right there. And so I could draw that rectangle here to here. I could also go on this side, 21, 1, 2, 3, 4, up to 4, which is right here, and draw the other rectangle right there. So go in the other direction. So there's 4, 21, and 21 and 4. Okay, our next one is at 7, length of 7 and a width of 18. So here's my 7 line, and I go out to 18. There's 15, 16, 17, oops, 18. Out to there, sorry about that. So 7 and 18 goes to that point. So we draw that down, and we pull that across there, and there's my 7/18. And I also go 18 here, 20, 19, 18, 7, 1, 2, 3, 4, 5, 6, 7, and put a point there, and just draw my line down for that rectangle for where it would be. Okay, so there's 7, 18, and 18 and 7. Looking good so far. I can do the 12 and 13. So I go up 12, 10, 11, 12, and I can go out to 13, which is going to be, let's see, here is 10. So 12, 10, 11, 12, 13. So 12, 13 can be here. And I could also do 13 and 12, which is going to be here, right? I didn't have that on my chart, but I can go ahead and do it anyways. That's 13 and 12. Very close together there, isn't it? And then to match my 15 and 10, right, I already had this 15 and 10 guy right here, or 10, 15. That's what I started with. I could also go 10 and 15 out to here, and make sure the right spot. Yep, let's get right there. And 10 and 15 like so. Okay, so there it is, all kind of graphed out there for what that would look like with all those points drawn to make a whole bunch of rectangles. Now, it says each rectangle has a vertex that lies in the first quadrant. True. These vertices lie in a line. Draw on this line and write an equation for it. So each one has a vertex that's inside this first quadrant. So they all share that right there, right? So if we take a look at it, it looks something like this. And this is what the line looks like that they want me to then write an equation for. It goes from there to there. Notice how they all have one vertex inside of the first quadrant, and that vertex is on that line for every single one of those rectangles. I think it's kind of cool to look at there. Now in terms of an equation here, we have to look in terms of y equals our rate of change, or constant, times x plus where it crosses the y-axis. Okay, we're crossing the y-axis here at 25, so I can say it's a plus 25 on this side. And now in terms of what's my slope going to be, I can see that for every time I'm going down 1 over 1, down 1 over 1. So my slope is going to be negative 1. And I can write it for now as negative 1 over 1, but that really, negative 1 over 1 is the same as just a negative. And I can rewrite it as y equals negative x plus 25. And we do that because there's always that 1 in front of it, even though you can't see it, right? So the slope of this line, we would say here, is negative 1, the slope. And how does the slope describe how the width changes and the length changes? Okay, so as the length decreases by 1, then the width increases by 1, is what we would say. So when the length decreases by 1, then the width increases by 1. And that's the big thing that we're seeing there. And that's what that equation is telling me in that picture. So a great little problem. I know it took a little extra time drawing it out there, but it's kind of cool to see how that works out and you get a nice line there. In terms of a summary here, we would say that horizontal lines, right? Horizontal lines in the coordinate plane represent situations where the y value doesn't change at all while the x value changes, right? That's going to be that y is going to equal some value, okay? And by doing that, we're going to end up with a horizontal line that goes this way. In the same way, over here, a vertical line represents a situation where the x value doesn't change at all while the y value changes. So that would be an x equals something like so. And so we would have a graph that looks something like your x and y, here's my y and my x, where you'd have a line that goes like that. Something along those lines there. All right, let's take a look at tonight's homework. Suppose you wanted to graph the equation y equals negative 4x minus 1. Describe the steps you would take to draw the graph, and how would you check that the graph you drew is correct? Well, the first step I would do is I would go ahead and I would actually draw a coordinate graph like this, okay? And I would probably look at my y-intercept, and I'd say, well, I know that's going to be a place where I need to cross the y-axis. So I would go ahead and start with that and say, well, let's label that negative 1. And I'd probably put a couple extra points down. I'd then go up about the same amount, 1, 2, 3, 4. And then I'm going to go out. Now, how far out I go, I look at that slope value. and I think, well, I'm going to have to go up 4 over 1 or down 4 over 1 because of the way it is. Because it's negative, I need to make some more lines going down. So I know I have to go down 4 at least, so I'm going to go down to at least -5. And I can come out here and add a couple more marks there to make that work. That's what I would do first. I look at my y-intercept, then I look at my slope to see how much further down I'm going to have to go. Now my next step would be I would plot my y-intercept point there. And once I have that in place, then I'm going to go ahead and look at my slope and go down 4, 1, 2, 3, 4, and over 1. And when I have my 2 points all put together, then I can take my ruler and pencil, whatever I might have, and I can play connect the dots and draw the graph like so. Now the way I would check if my graph was correct is I would select a couple points or coordinates to plug into that to see if it's accurate. So for example, this point right here is at 1, -5. That's the point that I marked right here. If my graph is right, I should be able to put the 1 in the place of x and end up with -5. So let's try that out real quick. Here I have -4 times 1 minus 1. -4 times 1 is -4. -4 minus 1 is -5. Does that equal that? Yes, it does. And so because it does, that's an accurate point, which means my graph is correct. All right, number 2. It says draw the following lines and then write an equation for each. So we're going to go ahead and draw ourselves a little graph guy here. Well, actually, I think I'm right. Yeah, you have one on the back. I did this in my notes too. You have grid paper on the back side. So here we go. Try this again. All right. So first of all, we have the slope of 0 and y-intercept is 5. So a y-intercept at 5 is going to be here. And if the slope is 0, then we would say that it has no slope and it just goes right across like so. The equation for this, okay, because as a y-intercept of 5, it's going horizontal. So we're going to say this equation is y equals 5. Okay? And I can write that over here as well if you wanted to. Y equals 5. The next one, we have a slope is 2. Slope is 2. And the y-intercept is -1. So I'm going to come down here at -1. And it says that my slope is 2. That means we're going to be going up 2 and over 1. Up 2 over 1. It's always good to get a couple of those together there if it helps you out a bit. And then we play connect the dots for up 2 over 1. Like so. Something like that, right? And we play connect the dots like that. And so that line there is going to be at y equals, and then we want to put our slope in, which is 2x, and then our y-intercept is -1. This is an equal sign, sorry, not a z. All right, so that's that one there. For number, so we put it here, y equals 2x minus 1. For the next one, we have y, the slope is -2, and y-intercept is +1. So we're at +1 here, and the slope is -2. So we're going to go down 2 over 1, down 2 over 1, right? So now I have a couple points there, and I put my marker down like this. I try to line that up as best I can. And then just connect my dots for a line like this. And we would say this is y equals -2x, and it's at +1 where it crosses the y-axis right there. All right, so that's that one. Y equals -2x plus 1. And finally, for our last one here, we have a slope is -1 over 2. The y-intercept is at -1, so we're going to start here. And our slope we said was -1/2, which means we're going to go down 1 over 2, down 1 over 2, down 1 over 2, right? And I can do this as many times as it takes to get it accurate or pretty close to where I need to be. And then I can line up my dots like so. And then connect the dots like that. And we're going to say that this is going to be y equals negative 1/2 x minus 1. We started at negative 1 right there, and we moved on. So y equals negative 1/2 x minus 1. So those are the 4 equations that I would come up with, and the lines for how that would work. Okay, so that's that right there. Got it. Now this next one here, I need to draw in one extra line because it didn't come out very well. You have several lines on your paper here. You have a line right here. I'm going to just highlight them in some orange for you so you can see them a little different, or peach. You have another line right here. You have another line right here. And there's actually a line right here that doesn't come out very well, my copy very well at all. Those are the lines that are on your paper. Okay? So now you have to write an equation for each of these lines. This line right here is at y equals 4 for where y is going to be at. So when y equals 4, we have this line, so we would say y equals 4. This line is at negative 1, negative 2, so we'd say this line is y equals negative 2. All right. For this one right here, we're at 6, and we're going vertical here, so we'd say this is x equals 6. And over here, we're at negative 1, so this line would be x equals negative 1. Those become the equations for the 4 lines on that grid right there. All right, and our last question, which is a review question from lesson 7. It says, a publisher wants to figure out how thick her new book will be. The book has a front cover and a back cover, each of which have a thickness of 1/4 inch. Notice it's each. So whatever this is, I'm going to multiply it by 2, because it's a front and a back. They have a choice of which type of paper to print the book on. Bond paper, A, has a thickness of 1/4 inch per 100 pages. Write an equation for the width of the book, Y, if it has X hundred pages, printed on bond paper. So, let's think of it this way. Our answer is going to be Y. Okay, we know that so far. We know that we're going to start off with the cover. Now our cover is going to be 1/4 inch plus another 1/4 inch, right? So when I add that up, I end up with 2/4, which is the same as 1/2. So I know I'm going to have 1/2. Not worry about the order here, but I know I'm going to have 1/2 for the cover. That's my cover. And I'm going to add to that then this inside the pages part. Pages part is what's a little bit more complicated, right? In this case, it's 1/4 inch per 100 pages. I don't know how many pages are going to be in the book, but I know that it's 1/4 inch per 100 pages. So I can write that as 1/4 x for that equation there. I can write it the proper way, or the way we've been working on it, that y equals mx plus b, right? That's the way we've been talking about it there. But I put it here first just so we could say cover plus pages. Let me rewrite it then. Y equals 1/4 x plus 1/2, just to get it in the format that you're probably used to seeing at this point here. When I look at the ledger paper one, it says ledger paper has a thickness of 2/5 inch per 100 pages. Okay, so same idea. We would say y equals, in this case though, we would go ahead and say 2/5 times x for the inside pages, plus what? Plus the cover, which is 1/2. So I already start with that thickness. That's my starting point already. For C, it says if they instead chose a front and back cover with thickness of 1/3 inch, right? How would this change the equation? Well, how would it change is this. Now, if I have 1/3 plus 1/3, that's going to be 2/3 for the front and back covers. That's going to change things quite a bit, but not tons. So let's say, for example, on my first equation, right, my first one, we call it letter A, we would change it to be y equals, the pages is still 1/4 x, but now we're going to add 2/3 to it. And for the B part, our pages are still going to be 2/5 x, but we're also going to add a 2/3 to it. So we changed the back number here to be a different thickness because of the cover being different as well. All right, hope that helps you out, and have a great day.